how do things roll? What do we mean by rolling motion? Well, here I've got something that rolls. And if I turn it on its side, and let me zoom all the way out so people can see it. Are you ready? Here's rolling motion. Let's do it again in super slow motion. Oh wait, that was the same. All right, so what's happening is an object is rolling. Now, let me kind of tilt it so you can see the thing. It's rolling on a surface. And we want to understand how rolling motion works. Because in rolling motion, which is what you do when you're riding a bicycle, right? Or a skateboard or whatever, the wheel is rolling along, and so you're translating. I mean, look at this thing. It's translating, but it's also rotating. And so we want to understand that. Yeah, we do. I do. Maybe you don't care. All right, so what I'm going to do is make a little mark right here. Probably should have checked this out before. Okay, so now I'm going to roll one complete rotation. Oh, and it goes off the, of course it goes off the paper. All right, it goes all the way over to here. All right, so this is the distance we traveled. This is how far we translated. Do you see this over here on the table? All right. So now how far is this distance? Or what was our displacement? Delta x right here. What is that equal to when compared to this? Isn't it? It's kind of like I'm taking the circumference of this circle, right? Yeah, very good. That was Anna. She did very good. All right. See what happens when you put your phone away for 10 minutes? All right. So we're going to go all the way around one time. It's like I took the circumference of this and I straightened it out. So delta x is equal to, well, what is the circumference of a circle? Goodbye, cart people. Huh? It's 2 pi r. You knew that, right?
Yes.
Darn tootin' you did. All right, now let's suppose. Okay. Now, let's just suppose that the velocity is a constant here. Okay. So let's just say, velocity equals a constant. Well, that's just going to be delta x over delta t, right? Well, delta x here is 2 pi r. And, but what's true about delta t? Well, it's a very special amount of time, right? If this thing is spinning, what do we call the time it takes to spin around one time? We had a name for that last time. Starts with a P. It's the period. So really delta t is the period, which we use a capital T to represent. Well, and this is the part I see. Anyway, what is 2 pi over the period? Now, okay, let me ask you this. How many radians did this thing go through? It went through one complete rotation, which is 2 pi radians. So I'm going to rewrite, this is kind of like 2 pi radians over the times r over the period. Now 2 pi over the period, we derived an expression for that. And that is our angular velocity in radians per second, right? 2 pi radians per second. So the angular velocity of something that's spinning is 2 pi radians over the period. Right, we go, if something is spinning, right, it'll go 2 pi radians if it makes one full rotation. So what I'm going to do is just substitute that and say, hey, my linear speed is equal to r times my angular velocity. In other words, when I have rolling motion, the speed of my rotating object, the translational speed, v, is just equal to the radius r times the angular velocity in terms of radians per second. And so now we can relate. This gives us a relationship between linear speed of a rolling object and angular velocity. And that's also, but if you also want to think of this as v is delta x over delta t is equal to r delta theta over delta t. You can see that if I let delta t cancel out, the displacement delta x is equal to the angular displacement in radians times r. Now this makes a whole lot of sense after our lecture last time where we related, because look, the speed that this object, it's just unrolling its circumference over and over and over again as it rolls. Okay. So it can be a little bit confusing, this little expression, but it really makes sense. And here's what you can do. Just take any round object, and here I have an asteroid. This is an asteroid from space, because you can tell I got it at the observatory, Lowell Observatory. Okay, and if I roll this thing, its speed, how fast it's translating, is related to how fast it's spinning. So this is how fast it's going, translating. This is how fast it's spinning, and they're related by r. But this must be in radians per second for this equation to work. So this is the only little equation we're going to use. This one, I kind of boogered this one up in the last lecture that I did for you guys, but this makes a lot of sense, right? 2 pi radians in one period is what I go through when I'm spinning. It's also related to my linear speed if I'm rolling. Now there are times where things are spinning and translating, but they're not rolling. Okay, and I'll show you an example of that. Like if, let's say this is the wheel of a car, and I'll kind of hold it side. If this is a wheel in a car and you spin out, and you start going forward, that's not rolling. That's, skidding to a stop or peeling out or something like that. Or if you're like a satellite that could be spinning and translating in orbit, that's not rolling motion. In order for it to be rolling motion, see this part right here? It has to not be sliding. The part that's in contact as it rolls, the part that's right here, that's in the part of the top here, this wheel, that's in contact with the table, it's not sliding or moving with respect to the table. Okay, that's what defines rolling motion. Okay. And that is all.